couple of minutes, say 1 or 2, and start?
Sure.
Yep. Yeah. I get the live stream going. It takes. Good. Okay, so we're live streamed on YouTube as well. Great, fantastic. Things going
Hello, everybody. You're all welcome to day 2 of the Biophysics in and for Africa Zoom conference. Today's first session is titled X-ray Scattering, Spectroscopy and Radiation in Biophysics. Our very first speaker is Ben Boyd from Monash University. His research focuses on drug delivery, disposition, and dynamics. Today, he will be talking about using scattering approaches to understand the behavior of drugs during digestion of milk and infant formula. So, Ben, the floor is yours.
Thank you, Emmanuel, and thank you to Simon and other organisers of the meeting, and thank you for joining us. It's a great opportunity to tell you a bit about some of our research. I've simplified the title just to Scattering Milk and Drugs, and you'll see why at the end that I've done that. So I'm located at Monash University in Melbourne, Australia, as you can see on the map there, a long way away from many of you, or most of you, I would say. So my research group, as Emmanuel's introduced, is interested in drug delivery, but we're actually mostly interested in lipids and what lipids do under certain circumstances. And in particular, you're putting my pharmacy school hat on, we're interested in what happens to lipids when they're used in a formulation or when they're taken with medicines. And so we can see in the top left-hand corner here, a schematic of what happens when we take lipids, whether they be as part of a pharmaceutical formulation or in food. And so we ingest the lipids, our body digests the fats in those lipids. So most lipids in our diet are triglycerides, and so the triglycerides are broken down by enzymes to form monoglycerides and fatty acids ultimately. And they're the components then that are able to be absorbed by our body. And so obviously we've known about that process for a long time. And what we've also known in physical chemistry is that when we bring these sorts of molecules together, these more polar lipids that you can get, different colloidal structures form in aqueous environments. So in our gut, it's reasonable to expect that if we're forming these more polar lipids through the process of digestion, that they're going to form these complex structures. So the one in the top left-hand corner we would call a cubic phase. Top right-hand corner is called a hexagonal phase, and they're really interesting to us, partly because of their formation during the digestion of lipids, but also we can use them as a delivery system in their own right because we know they provide a slow release effect for drugs. That's not really the context of the talk today. What I want to talk about is the formation of these structures during digestion and then some of the consequences for drugs that we might co-administer with lipids in our diet, and in this case, as the title would have suggested, talking about milk and infant formula from a pediatric drug formulation perspective. So these lipids can assemble to form different structures, and in physical chemistry we know the types of structures that are likely to form, or at least the trend in what those structures might be as we change the geometry of the lipids that are formed. They can form some interesting structured particles. And as I mentioned, we're interested in what happens then when a drug's incorporated into that process. So how does the drug then get dissolved into these colloidal structures and ultimately be available for the body to absorb that drug. So that's sort of the context, or setting the scene, if you like. So in order to study what happens to lipid formulations, and the lipid formulation could be a pharmaceutical formulation, or it could be milk, as we've implied. So we would use what we call an in vitro lipolysis model for that. This is quite common in the pharmaceutical industry, and it's quite common in the food industry to use as a way of understanding what's happening during the digestion process of lipids. And so this is set up with a feedback loop so that we can track the kinetics of digestion by the production of fatty acids. And in past times, we may have taken a sample of this medium while it's digesting and try to separate out the drug, or measure some property of that complex digesting mixture. The problem with taking samples from these systems is we then need to process the sample, and there's a time delay involved in that, and you may miss some information. So if we're interested in understanding what the structures are that are forming during the lipid digestion process and concurrently what's happening to the drug, then we need an in situ measurement in order to do that. And so I guess what our group's become quite well known for now is having taken this model and then pumping that digesting mixture through a capillary and using X-ray scattering as a mechanism or as a technique to probe what's happening at the structural level within that digesting mixture. And I'll explain the technique in a moment for those that aren't familiar with X-ray scattering. But we use the synchrotron source in Melbourne. So this is in Melbourne, Australia. It's always nice and sunny in Melbourne, except for today. And so the Australian synchrotron is just next to the Monash campus. So we're very lucky to have that light source in Melbourne and largely at our disposal to generate these kind of new techniques and new approaches. So this one's fairly simple. So we plumb in our in vitro model and we interrogate what's happening to structures that are forming in those digesting systems over time. So a little on small angle X-ray scattering first of all. So we have our synchrotron source. We could use a lab source, but it's not sufficiently intense or high flux in order to acquire enough scattering on the time scales that are relevant to digestion. So we need to be understanding changes in the system on the scale of seconds to minutes, not hours like we may have to rely or may have to suffer in the case of a lab instrument. So that's why we use the synchrotron technique for these sort of studies. So if there's ordered assembly of the lipids, so the cubic phases, as I mentioned before, or the hexagonal phase, if there's ordered assembly of the lipids during that digestion process, then we'll see the characteristic diffraction patterns arising due to those different structures. And so that allows us then to track changes that are occurring on that second to minutes timescale using synchrotron source as the analytical technique to understand structure over time. I'll talk a little bit later about how we use that then also to track what's happening with the drug. So firstly, we'll go to milk, and so milk, as we know, we'd call it the ultimate lipid formulation in a pharmaceutical context. So we survive on it for the first 6 months of our lives generally, or longer, depending on location and culture and health. And so we know that 3.8% of milk roughly is fat. So if we're talking about cow milk in the first instance, and the majority of that is made up of those triglycerides that break down to form those polar lipids. And so if we apply our scattering technique to those polar lipids, at least to milk as it's being digested and as the polar lipids are being generated, so we can see we start with almost no scattering, no interest in scattering at least. But we can see that over time, as the triglycerides, or as the milk's digested and the triglycerides are digested down to monoglycerides and fatty acids, we're seeing these diffraction peaks arise and then disappear, and then different diffraction peaks arise that replace those peaks. So that's telling us that we're having dramatic changes in the structure of the fat droplets in the milk during the digestion process. And so we're seeing that some structures are formed and then disappear. So this is on replay now. So this main sort of peak here is due to some calcium soap formation, but in in this part, we're seeing an inverse micellar cubic phase appear and disappear. Then we see hexagonal phase appear and disappear. And then we're ultimately left with what we call the bicontinuous cubic phase, which was the one that was on the far left on the previous slide. So we can see those changes happening in real time during digestion of the fat. And we know that we're getting to around 95% or more of the fats being digested in these experiments. So we're left with those highly structured particles at the end that are the fat droplets. I've got cryo-TEM images, but I didn't put them into this talk. So you'll have to trust me that they form these highly ordered droplets with interesting textures when we're at the end of the digestion process. So this is taking that video where we've got the time-dependent scattering along the base here, and you can see the time scale. So this is over an hour. So we're digesting the triglycerides and we're forming those different structures. We end up at the end of the digestion process, we have these bicontinuous cubic phase particles. And very briefly, in a sort of biophysics context, or a physical chemistry context, this is the order that we see the structures form in is very much what we would expect from consideration of the packing constraints of the lipids. So as we go to the more and more polar lipids, we expect the structures to form in a more or less known order of appearance, and that's reflected in what we saw in that video. So the digestion of milk is a really nice validation, if you like, as I put at the bottom there, of the critical packing parameter concept. So that's really interesting. So that's cow milk, and that digests and forms those really ordered structures. So does it actually matter what sort of milk it is? Does it need to be milk at all? Could it be like soy extract, for example? And so if we take soy, so-called soy milk or soy extract, and we do the equivalent experiment, so we're digesting this under exactly the same conditions, same equipment and everything. So and it does not form those highly ordered structures. So the lipids that are present during the digestion of milk are really important in forming those highly ordered particles during the digestion process. And the lipids that constitute soybean oil effectively don't form those types of structures. So is it more or less a generic thing for mammals? And I haven't got time to show you all the data, but it turns out that cow milk, horse milk, dog milk, goat milk, and even human milk all form these highly ordered liquid crystalline structures during digestion. And all of the vegetable sourced extracts called milk, often called milk, do not form these highly ordered particles. So there's an interesting differential there. So we were also interested then in what happens with infant formula being kind of somewhat in between, and you often see this sort of marketing around infant formula that it's intended to completely mimic what's happening in human breast milk, and that's used probably as much as a marketing ploy as it is anything. And so to cut to the chase on the milk front, on the infant formula front, so this is 4 different infant formulas that we've digested under those same conditions, and so we can see the take-home message is that all 4 of them are different. So we have an inverse micellar cubic phase formed by this infant formula 1. It turns out this one's actually the closest to the behaviour of human breast milk. Infant formula 2 is slightly different, but it still forms this highly ordered cubic hexagonal phase, and then the other 2 don't form those ordered structures at all. So it does matter which infant formula we use, and they're all different because they all have different lipid profiles and different lipid compositions. We've done lipidomics analysis on all of these, and we know what components are doing essentially the heavy lifting to form different sorts of structures, and that then provides a mechanism to target certain compositions to get that sort of behaviour. So quickly sort of moving on to what happens in the case of drug particles. And so drugs when we incorporate them in these systems. And so, so we've had a project with the Bill and Melinda Gates Foundation for quite a while now to look at those, how does those digestion sort of processes and phenomena impact on what happens to drug in these sorts of systems. And so if we take our drugs and put them into milk, and we do these sort of digestion experiments, what can we learn from that? And I'll get onto in a moment the sort of really neat part of what we're doing in that area. But just to kind of set the scene with Gates Foundation on one particular sort of strong example. So artefunenal or OZ439 and ferroquin's a combination of two anti-malarial drugs that has been shown to give a single dose cure for malaria. So one tablet potentially, or one dose of the two drugs in the right combination, so the right dose of the two drugs can give it sufficient exposure so that you can get a single dose cure for malaria. So you don't have to have a course of treatment that can be problematic in many situations in Africa and other places. And so the catch is that when these drugs were put through clinical trials, a wide range of different formulations were tried. So different things were administered with the drugs in order to take them. So water, skim milk, juice, some horrible surfactant-based formulations, and full cream milk. And the only formulation that provided sufficient exposure to get potential therapeutic full efficacy was when the drugs were given in full cream milk. And so the bioavailability then, they know that we need a certain threshold up around this sort of 25,000 in AUC in order to achieve an effect. And so even with soy milk at the same fat content, you still don't get sufficient exposure to expect to reliably get a therapeutic effect. And so why is that, and what does it mean, was really the questions that the Gates Foundation came to us with. And so, as we've sort of I've mentioned before, so milk's mostly, or the fat in milk is mostly made up of triglycerides. And so we're not the first group to have thought about milk as a lipid-based formulation. So if you've got drugs that are soluble in lipids but not soluble in water, then they're often the really problematic ones that need a formulation approach. And so milk might be quite a logical place to go because, as I said, it's the ultimate lipid formulation from nature's perspective. And so it's surprising that it hasn't got a whole lot of attention in the pharmaceutical area as a potential way of formulating those sort of drug compounds. But the problem is that traditionally it's been approached from the point of view of how much drug can we dissolve in milk? And the answer to that is often not enough or not much, because when you have intact triglycerides, they tend to provide a much lower solubility than when you have the monoglycerides and fatty acids that are produced during digestion. So now that we know that milk is digested and it forms those polar lipids quite readily, and they interact with each other and form those structured droplets, we started to think about it. Well, actually, it doesn't matter whether the drug's soluble in milk or not before digestion. What's important is maybe the digestion process itself, and so does digestion then enable the drug to be dissolved and then be available for it to be absorbed? And maybe that's the reason why the milk as a formulation was so successful during the clinical trials and not the other formulations. So what happens if we have milk, the drug in with milk during digestion? So this is where the scattering studies become really interesting. I think they're interesting for milk forming those different structures, but it becomes really interesting because in the same experiment, we can then look at the wider angle scattering and look at what's happening to the drug particles. And so if we have solid crystalline drug that's not dissolved, then that drug's not available to be absorbed. And we know with a lot of those drugs that, you know, that they're not very soluble in milk, as I mentioned earlier. And so maybe, well, not maybe, but what we know that we can do then is use the sort of signature diffraction peaks for the drug as a way of tracking where the drug's being dissolved into those digesting milk systems. So we can have our in vitro model here with milk or infant formula, and in this case have drug mixed in. And if the drug's not soluble, then it's going to be there as a crystalline suspension floating around in the emulsion. And perhaps we can pick up changes in the diffraction pattern over time in the sort of wider angle region where we would see those diffraction peaks due to the drug, not due to the lipid. And so for those that are not scattering people, so when we talk about smaller and wider, smaller angles are probing larger structures. So wide angle is applicable to looking at molecular level packing in crystals, and that's why we talk about using the wider angles to look at crystal structures. And so if we do that sort of an experiment where we have it in flow through and we're looking at the diffraction over time during digestion of an emulsion like milk, then we can expect that three things may happen. So if the drug's already dissolved and then it precipitates, then we might see appearance of characteristic diffraction peaks that represent the crystal structure of the drug particles as it's precipitating. We might see disappearance, which is what we really want. So we want to, in the context of drug delivery, if we want to use milk and digesting milk in particular as a means of dissolving the drug so that it's then available for absorption, which is what our hypothesis is around what's happening with OZ439 and ferroquin, then we want to see that disappearance of drug peaks over time. Or a third thing that might happen is we might actually observe a polymorphic transformation where we see the solid drug particles transform from one crystal structure to a different crystal structure. And I'll actually show you an example of that as well. So that's the power of this approach, is that in real time we can track those processes concurrently with seeing what's happening to the lipid self-assembly as well, so we can sort of correlate changes in structure ultimately to what's happening to drug. So just as one example of that, so this is scenario. This is not an anti-malarial drug. This is just an initial example to show you the sorts of data that we can get. So if this is a diffraction pattern for cinnarizine and we track, let's say, the intensity of the main peak here, then it's in suspension in undigested milk. So if we stir for a while in milk, we don't lose that crystalline structure. So the drug doesn't dissolve into the undigested milk. But then if we add lipase, then the milk starts to get digested, and the drug then is ultimately completely solubilized into that digesting milk. So that's the sort of experiment that we can do, and so I'll show you what happens now when we do that for ferroquin and for OZ439. So we look at ferroquin first. Then, so this is the structure of ferroquin, interesting drug. And if we look at this peak here and we track the changes in the intensity of this diffraction peak, then if we just stir in milk, so stir the drug at a relevant dose, relevant to sort of taking the drug with a glass of milk, then we see a little bit of a drop in intensity. So the drug has some solubility in milk, but not much. So there's still a lot of a lot of insoluble drug present, and actually it does start to go up over time because there's a slight polymorphic transformation. There's a new drug polymorph that appears when you stir milk, ferroquin in milk. But as you can see, if we then inject lipase, we can completely solubilize the ferroquin in digested milk. So very strong solubilization effect very quickly for ferroquin in digesting milk. And so if we then look at OZ439, it's actually much more complicated. So OZ439, we call it the problem child because it undergoes a range of different behaviours that we'll talk through here. So initially it's a mesylate salt, and the reason that it's made as a mesylate salt is that it has extremely high solubility in water as a mesylate salt, and it turns out that it's actually forms micellar structures in water in its own right. But as soon as you put it into any physiological environment, if you put it into a gastric medium, then it precipitates immediately as a polysoluble hydrochloride salt. Or if you put it into a neutral environment, such as a small intestine, then it'll precipitate as the free base form. So it's only when you dissolve it in water that salt form is actually useful. And it turns out that as soon as it encounters any other environment, it completely precipitates anyway. So it's an interesting case study on historical pharmaceutical drug development. But anyway, it was developed as a mesylate salt, so that's what we have to work with. And so if we put it into a gastric environment, it precipitates, and that has a different scattering pattern to the mesylate form. And then if we neutralise, the free base form has a different scattering pattern again to the hydrochloride salt. And so we can actually track that process. I haven't got the data of going from the hydrochloride to the free base form. But the thing that's of more interest perhaps with OZ439 is that if you then digest OZ439 after it forms a free base form in milk, so you digest the milk, it actually will precipitate as another less soluble form again. So this, what we call this free base 2 form. So it's a transformation from one free base form to another free base form. And I don't know of any other technique that you could use to detect this. You may be able to detect it using Raman, but you need to know a priori that you're actually looking for a different polymorph in that case. So if we then look at the intensity of those diffraction peaks, then we lose the free base 1 peak, we gain the free base 2 peak, and if we keep digesting, then we do solubilize a fair proportion of the free base 2 form, but we never quite get to complete solubilization. And so that's different to ferroquin, remembering that ferroquin is completely solubilized during digestion of milk. So with OZ439, we must be able to absorb enough or dissolve enough because we can get enough for a therapeutic effect. But maybe we can actually do better if we have a more optimal system. So we discussed the option of perhaps looking at infant formula as a possible solution because, as I mentioned before, infant formulas have got different lipid compositions, and they've also got different. We can tailor the ratio of fat to drug using infant formula just by changing the amount of, say, powdered drug and powdered infant formula that we put together. And we also have the benefit that milk is highly variable, very difficult to think about a process by which you might be able to get milk sort of registered as a formal excipient in a drug development context, whereas infant formula is highly regulated, and indeed we're actually going through that process with the FDA at the moment. And so so the question was, well, how do infant formulas behave compared to milk, and does that help us in our ultimate goal of trying to solubilize these drugs? So just as a reminder, all the infant formulas are different. So what do we see? So if we have ferroquin, so now I'm slightly changing the way the data is presented. So now we're looking at the intensity of the bars is like the intensity on those graphs versus time. But we're just looking at the end point of digestion, how much of the drug is left in the crystalline form. So what we want to see is very low bars. So that means that all of the drug's being solubilized at the end of digestion. And so as we saw with ferroquin in milk, there was no drug left as crystalline drug. So the milk is this dashed line at the bottom. And if we take 3 of those infant formulas and look at them with increased fat content, then in all cases at all fat contents, essentially, they're almost completely solubilize the drug. So there's no problem with ferroquin. You can put the ferroquin with a very low proportion of infant formula, and it almost doesn't matter which infant formula it is, you'll get complete solubilization. beautiful drug from that perspective. So as you can imagine, the problem child is not the same scenario. So as we saw earlier, we don't solubilize all of the drug. We solubilize around 50% of the drug in the case of digesting OZ439 in milk. And so it turns out that the way to read this graph is that, so the fat content of milk's about 3.8%. So we have infant formula at a lower fat content, then infant formula 1, even at a lower fat content, is much better than milk. But the other two are at no better or worse. At a higher fat content, all of the infant formulas are better than milk. The infant formula 3 only better, and infant formula 1 is way better. And then if we look here at this ratio of infant formula to drug, we're getting complete solubilization of OZ439. So we can see there we've got complete solubilization of OZ439. We've got complete solubilization of ferroquin. So that's what we want to see. We want to see both of those drugs be completely solubilized, and that during digestion. And that then is a good indicator that we're likely to get good bioavailability. So I'll skip the next two slides. That's just saying that we can start to sort of marry up some of the changes in lipid composition as we during digestion, and understand which of those lipids is really doing the heavy lifting in terms of drug solubilization. But the upshot of it is that if we use now that particular infant formula at that level relative to drug, that we indeed can get bioavailability that's as good as the milk formulation, and potentially with less fat than with milk itself. And that's actually been taken into the clinic now, and there's been a bioavailability study that shows that composition outperforms soy and reaches the sorts of exposure levels that we would then expect in a clinical efficacy study, should provide that long sought after single dose cure. So I just wanted to show one other relevant example where we see similar behaviour. And so this is clofazimine, which is in the past it's been used primarily as a anti-TB drug and in treatment of leprosy. And it's actually been found to be quite effective against cryptosporidiosis. And so, again, the Gates Foundation was interested in knowing, would milk or infant formula be a way of speeding up and enhancing the solubilization of clofazimine if it was to be used in that cryptosporidiosis type application. In this case, you don't really want the drug necessarily to be absorbed. You want it to be just available in the intestine, because it's the intestinally sort of resident parasite. And so so we can see on the left-hand side, so the left-hand side's telling us what happens in the case of milk. And so if we just stir it in buffer, then we don't get any clofazimine solubilized, because it's not soluble, it's not a soluble, water-soluble drug. Likewise, it's not soluble essentially in milk. But then if we digest the milk, we see that trajectory of solubilization again that we've seen previously with OZ439, and even more spectacularly with ferroquin. Then if we do the same experiment with infant formula at increasing concentrations of fat, then we can see that in all cases we're getting a reduction in the amount of crystalline clofazimine that's left. And it does matter what the fat content of the formula is in that case. So we can think about an optimal level of formula to go with our drug in that case, in order to get maximise the opportunity for clofazimine to then act once it's in solution. So some overall summary. So a few takeaway points as I finish up. The digestion of milk yields these highly ordered self-assembled structures, and the lipid composition matters. And it can lead to changes in the way that the systems interact with co-administered drug. So digestion's a powerful driver. You often need that digestion to drive the drug solubilization in these sorts of systems. Milk's good, but infant formula is probably better only in the context of drug solubilization. I'm not advocating for infant formula at all in its role in infant nutrition. That's not my area of expertise, but it certainly does have some attractive features with respect to providing a potential dose form, solid dose form that's not a liquid, and avoids all of those stability issues and variability issues that you might expect if you tried to make a product based on milk. And this is our team that's working in this area. So Adrian's the beamline scientist at Australian Synchrotron. Until very recently, he's actually project managing on secondment some new beamline installations at the Australian Synchrotron. And I'd like to particularly thank the Bill and Melinda Gates Foundation and Mia Bowers for funding and for advice during the project. And thank you all for your attention today.
Thank you very much, Ben, for this very interesting talk. We do have some time for a couple of questions. Please, if you have a question, you can indicate by the reaction button to raise your hand.
You may need to take any questions, Emmanuel. I can't see the screen.
Oh,
to tell you the truth, I cannot find the raise your hand button, but I see the clap button. But I did have a question. I have a question. What is what type of flux do you need to do these experiments from the beamline?
So the beamline absolute flux I haven't got off at the tip of my fingers. So because we've got this in flow through, we can basically open everything up and let it go. So we're usually running at 100% flux, no attenuation, and we don't see any sign of beam damage because we're in a continual flow through loop.
Gotcha.
And the actual total amount of material that ever sees the beam is relatively small. And I should say that these are 1 second acquisitions for this level of either 1 second or 5 seconds, and it doesn't really matter for this level of information that we get from those scattering profiles. So we're running at pretty high intensity. I think I'm thinking 3 by 10 to the 13 photons a second rings a bell, but I wouldn't want to be held to that.
Okay, thank you.
So I do have a question. How will the solubility of a drug for an adult compare with that of an infant, because an adult have probably more complex nutritional requirements?
Yeah, that's a good question. So we know that the contents of the infant gut is slightly different to adult, but in terms of it's very age dependent, obviously, because bile and the gallbladder contractions that you have as an adult are less frequent in a child. It's more of a continual flow. It's more like a rat, actually. So rats have a continual bile flow into their intestine, whereas adult humans have a pulse. So the basal levels are not very different, but if we have a fed response, so if we had a large glass of milk and get a gallbladder contraction, then I think it would be quite a different story. So we're yet to do any sort of formal pharmacokinetic study actually in children with these systems.
All right, thank you very much. Let's give Ben a round of applause.
Thank you.
Thank you, Ben.
So we move to the next talk, which is from Dr. Damilola Samson. He's going to be talking about radiation attenuation properties of natural product-based adhesive bonded rhizospora particle boards for tissue substitute phantom applications. Wow. The floor is yours if you're there.
Yeah, good evening, everyone. Please,
Hi.
can you hear me?
Yes.
Okay. And my slide, can you see my slide?
Not yet. Can you share your screen?
Okay. Can you see it now?
Not
No.
yet.
So you're a co-host. So you have the ability. There's a green button at there you go. There we
Okay.
go.
You've seen it now.
Yes.
Okay, thank you.
And I think if you go in presentation mode, we should see the whole thing.
Yeah, good evening. Yeah, from Malaysia, Penang. It's been a privilege to be part of this physics week from Johannesburg. My work is based on the radiation attenuation properties of natural product-based adhesives bonded Rastafari species particle board for tissue substitutes phantom application. The word the natural product here mean is a bio-based adhesive material. And the Rastafari species is a form of species which is morphologically and is adaptive in characteristics, and they have a suitability, and they have undergone a lot of scattering and also radiological application. And since we know that the water on its own, we know that water has always been referred to as a reference material, that is a reference quality assurance material. But it has also been noticed that water on its own cannot be served as a quality assurance reference material. Then the word has not been agitated for a tissue substitute phantom material. Now, the presentations outlined focus on the introduction, significance, and the objectives of the research, the methodology, the result, and the discussion and conclusion. Now, we know that lately the need for phantoms material to precisely mimic the human body for those simulation calculations has become progressively apparent. Then the use of water is not always feasible as a reference quality assurance due to its liquidity and incompatibilities of some radiation dosimetric tools. Then now, we now look at the sense in this form that tissue substitute phantom material will provide good simulations of free human tissue as well as aid in the development and the validation of the modality in medical application. Then there are lots of tissue substitute material, lots of research work has been done on the form of tissue substitute material like the solid water, the PAPS. Then, and also it has also been noticed that due to the variation and elemental compositions of this material, commercially available water substitute material, they lack the capability to produce good simulations to water and the soft tissue. In this regard, phantom made from Rastafari species composites have been found to demonstrate satisfactory characteristics. As I said earlier on, Rastafari species has a morphological, physiological adaptation, homogeneity, and also malleability. In conventional medicine, Rastafari species has been used to treat agunax, boil, leprosy, fever, malaria, fungal infection, etc. Then also it has been used in the building industry and also in the case of for making of particle board, fiber board. Then now, and then we know that Rastafari on its own cannot be, the untreated Rastafari also have its own deficiency, that is the disadvantages. Then we now look at it that the best thing is for us to be able to cure this Rastafari species, that is by treating it with an adhesive. Adhesive bonding of wood has been a key factor in the successful application of the raw materials in the wood industry. And this adhesive can be reversed into two. They either be a bio-based or naturally based adhesive or renewable-based adhesive, or the adhesive can be a non-renewable or it's a synthetic or a petroleum-based adhesive. But due to also the negative effect, negative effect of the synthetic-based petroleum-based adhesive, which has shown chronic toxicity, malignant leukemia, mortality, then we then look at it that the next phase is that to use the bio-based adhesive, which is naturally based. Then among the naturally based bio-adhesive, soya protein, which comprise of three types, the soya protein isolate, soya protein concentrate, and the fatty soya flour have already been widely regarded as an alternative bio-based wood adhesive in industrial application. Then on its own also, soya protein on its own cannot also be able to satisfy the standard, the characteristics of water as a phantom material. Then we now also have to be able to add a cross-linking material into this water, into the soya protein. Then the cross-linking material that as they use, different techniques as they use, then among the different techniques, the chemical cross-linking has been the most reliable, in which sodium hydroxide and interconnect acid epichlorohydrin has rendered it appropriate material to improve the radiation attenuation property of particle board made of Rhassophora species as potential tissue substitute phantom material. Now, the significances of the research, this is the first studies to optimize the characteristics of Rhassophora species particle board manufactured using soya protein concentrate, soya protein isolate, sodium hydroxide, interconnect acid as a suitable solid tissue substitute material for dosimetric work in medical health application. The importance of this work developed in this work is to contribute to the construction of high-quality particle board pattern with comparable radiation attenuation parameters to water and other substitute commercial phantom material. Now, why we use the interconnect acid in this sense is just because that the interconnect acid is considered as one of the top valued added building block chemical that can be produced from sugar. One, it consists of N3-chloro-2-hydrophylline and also azimuthal ring functional group that could effectively react with amino acid group, carboxylic acid group, and other nucleophilic group in SPC, SPI, effectively cross-link the adhesive, thereby allowing cross-linking agent dosage reduction. Okay, now the objective is to investigate the effect of sodium hydroxide on SPC, SPI-based adhesive with different substitution rates of IEPPAE resin. The substitution rate that we've taken note of in these studies is at 0%, then at 10 weight percent, and also at 15 weight percent. Then the next phase is to develop and also evaluate the effective atomic number, the radiation attenuation parameters of modified SPC, SPI, Rhassophora species particle board phantom under low and the high energy photon. At the low energy range, we have 16.59 to 26.25 keV, and also at high energy range, we have 0.622 mega electron volt to 1.25 mega electron volt. Now, methodology. The first phase in the sample preparation is to ground the Rhassophora species into and also segregate it into different particle size. We are considering 3 different particle size. Then now we have to also, the next stage now is to mix 25 grams of the SPC, then with a distilled water, we vary the variation of the distilled water, stir it for 30 minutes at room temperature. Then we add the substitution rate of interconnect acid into it. Then the next phase is now to add sodium hydroxide to it, 10 weight percent of sodium hydroxide, and stir it for 30 minutes at room temperature. Then also for the case of the SPI, then 12 grams of dry powders of the SPIs added into the still water, also vary the concentration. Then stir it for 30 minutes at room temperature. Then we have different substitution rates of interconnect acid epichlorohydrin. Then also, we also ensure that the pH values was being established at 11.0, since our focus is to be able to produce a bio-based material. Now, fabrication of the particle board. Then at the fabrication stage, now we make use of a cylindrical mold. Then then we now ask to compress the material. After the mixtures, we compress it, then at 0.49 megapascals, then at room temp at 0 degrees Celsius for 5 minutes, then hot press to produce a particle board at 20 megapascals, 175 degrees Celsius, and 80 minutes. Before we can do this, we've already did the TDA on it so that we can be able to know the onset temperatures. Then now this is not the particle board that we will fabricate. Now the theoretical calculations of average density and also the effective atomic number. This is the equation that we use to calculate the density, then where M is the mass, L is the length, the weight, and also the time. Then we also have to get the errors in the density, and then we make use of this equation to calculate for the effective atomic number. Now, the radiation attenuation parameters low energy photon we make use of the Srf setup by using americium 241 as the source. Then we have pneumobium, then molybdenum, palladium, and the tin as the metal plates with their varying energy. Then this is the equation that we make use of to calculate for the mass attenuation coefficient Then also, since we are dealing with a mixture of a material, we make use of the mixing rule. Then we now use this equation as to calculate for the mass attenuation coefficients for the mixture. Then we have to calculate the R value layer and also the framing part. Then now this is the setup for the Srf setup. Then the first phase on this setup is that the sample is being imposed. Then we have the ammunition source. Then now we have the metal plates. That is the niobium, molybdenum, palladium, and also the tin. Then an S-trace is being sent to it with different metal plates energy. Then from there now we can be able to get the rays of light, that is the incident rate imposed into it. Then we now have the rays that being formed. Then now, when this is being activated, then we can be able to see that the rays that is being imposed in it now determines the amount of ray that is going to be formed. Then the next phase is that we calibrate this. Then the calibration graph now also tells us that the analysis of calibration data indicate good approximation of SRF. Then which is also shown its accuracies with a R squared to be 0.999. Then now at high energy using the London setup, then we have section 137 with an initial activities of 0.037 gigant becquerel and also with the energy of 0.662 mega electron volt and the cobalt 60 with also energies of 1.25 mega electron volt. This is the London setup and this is the experimental stage, and we also seen from here that the calibration curve for the linear setup indeed is also a good approximation. Now, the results now is this: the average density that we use to calculate, because this is all our sample, then we compare it with water, the solid water, the soft tissue, and also the purpose. Now, the densities in this sense now are able to see that our phantom indeed has a similar values of density to that of water. And then we can also see from here that all the elemental compositions that are in tissue substitute phantom material are also in our fabricated phantom. Then also we also take notes from here also that the Z effective values also of our materials indeed is being suitable with that of water and all other tissue substitute phantom material. And then we can say that the differences between our values with those of water then is simple a range of 0.028%. Now we now have to plot the graph for the mass attenuation coefficient at low energy. At low energy stage, we found out that the A15 prime and also the A15 prime for the S species is very closer to that of water. Is closer to that of water, and then we shows that less energy dependent behaviors and they gradually decrease with increasing scatter gamma energy, which displays the increasing total interaction. Then we also, at SPI also, we found out that also B prime, that is at 15% this time, substitution rate of IPPAE, then the B15 prime is still indeed closer to that of water. Then at R value layer, because we know that the lesser the R value layer, then the more absorptive is the material. Then they found out that also that our material is still also closer to water for the SPC, and also at the B15 prime still also is closer to that of water. Then also the mean-free part also at low energy photon. Then we also take note that increasing the energy range also, as the energies increase, then also the mean-free part also increase. Then we can see from here that the values for A15 prime then is closer to that of water, which is the least among the studies sample, and also for SPI also, the B prime also is the least among the studies sample, which is close to that of water. Then we found out that the variations of the mean-free part, then the R value layer of A15 prime and also B15 prime are much smaller, and there is a good agreement between this and also that of the water. Then now we need to be able to know how suitability our sample is. Then we perform the t-test of the mass attenuation coefficients of our sample, then and come in related to that of water. And then we found out that that the p-values of our sample is greater than 0.05, for that of A15 prime and also B15 prime to be 0.071 and also 0.7 0.073. Then we now says that A15 prime prime and B15 prime prime have the highest mass attenuation coefficient, resulting to greater probabilities of photon interactions with enhanced absorption property, and it not significantly change because the B values indeed is greater than 0.05, agreeable to that of water. And also the lowest HVL and FPL imply that SPC and SPI with small material thickness will absorb the radiation. Then now at high energy, we still also have to graph for the high energy for the case of the cobalt 60 and also cesium 137. Now in calculating this now, because at the calibration stage, we still have to make use of barium 133 for the calibration. Then we also take note that at high energy, then increasing in the energy then leads to decrease in the mass attenuation coefficient. Then we also take note in this sense that decreases not leads to this indeed simply signifies that the incoherent scattering process which become the dominant at this stage. But for the case of the low energy stage, then we found out that the photoelectric effect indeed is the dominant at that stage. Then for high energy stage, then the incoherent scattering, that is the Compton scattering, and also the peer production, because which are in this energy range are simple the dominant. Then the same thing also happened in the case of HVL. It was noted that increasing in energy also increased the HVL, and that of B15 prime prime and A15 prime prime are also suitable to that of water. They are related to that of water, which having a similar scalarity with respect to that of water and also the solid water pattern. Then also for the case of MP, the mean-free part also, we also have a similar value. Then we now
can you wrap up your talk?
Okay, now the next phase of what we now do is to also find the similarities between that of water and also at high energy state, we perform the chi-square test. Then we found out that the chi-square test for A15 prime prime and also B15 prime prime then is less, and which is also closer to water. Then now from our result, it shows that a reasonable agreement for the two types of soya protein adhesive with 15% weight of high PPA is solid water per ton and the theoretical values of water. And they also found out that A15 prime prime, B15 prime prime display optimal quality value among the selected sample. And now in conclusion, we found that A15 prime prime, B15 prime, with that is 50% weight of interconnected acid perchloride with almost all the elements present in human body tissue display substantial massless performance when compared to other substitutes formulation. The result also indicate that good similarity between the effective atomic number and the radiation attenuation parameter with those of water and also other commercial photon material. Consequently, sodium hydroxide interconnected acid with 15% weight cross-link system will simultaneously reinforce and soften the SPI, SPC, phosphorus of photon, and they could be used as novel tissue source photon material for dosimetric computation for medical earth application. Thank you.
Thank you very much, Samson, for the talk. Probably have a minute for a couple of questions. So if you have a question, just unmute yourself and ask Samson.
Did you register? Hold on 1 second, let me check something.
So if there are no questions, then we can probably leave the question later on in the chat if there's anyone who wants to contact Samson.
Hold on, Amadou.
We now move to
Please, in case of no question, can I just chip in something?
Yes, please.
Yes, because the similar question from most of interaction that we have with people, they always ask us that why are we using 10% sodium hydroxide solution? Then also, why do we leave the interconic acid perchloride at 15%? Why not increasing it to 20%? Okay. Now, the answers to these two questions, the first question is that why 10% sodium hydroxide solution? Or why is it that we didn't use other alkalized liquid? Okay. Now, for the first one, we leave the pH values of the sodium hydroxide. We need the pH value of the sodium hydroxide because our focus is to produce a bio-based material. That's why we use the 10% sodium hydroxide solution, because it's the ultimate condition for cross-linking reaction as an effort to produce the bio-based material, so that this could be able to accelerate the solution hydrolysis and thus develop high bonding strength in the particle board pattern. Then now, why do we use 15% of IPPAE? We have did a series of substitution rate. And then before we can be able to base on that 15%, then it simply implies that it provides the most optimal result compared to those of other substitution rates. Increasing the concentration of IPPAE above 15%, however, we found to result in a deterioration of the physical and the mechanical characteristics, with only a slight improvement in dimensional stability parameters of the particle board pattern. And then this could lead to a weak interaction with the protein matrix and the added disadvantage of the particle board pattern becoming more acidic. Okay, and because these are the basic characteristics of a synthetic and also petroleum-based adhesive, then because now we want to produce a bio-based adhesive, that is why we have to ensure that we limit the concentration of the interconic acid, and then we'll be able to say that the optimum concentration of the interconic acid is simple at 15%, 15 weight percent of interconic acid, and which will be able to give us the optimal result. And then also we've seen that from the characteristics of the effective absorbing number, then the mass absorption coefficient at high energy and the low energy range be able to give us a similar result with respect to that of water and other tissues to Fatons material.
Okay, thank you very much for that. Yeah. We now move to the next speaker, who is Ibrahim Bello from Ahmadu Bello University. And the title of his talk is Radiological Assessment of Cement Particles from Obajana Factory. Ibrahim, are you there? Could you please share your screen?
I don't see him.
Okay, so we can move to the next speaker. If he comes, then we can slot him in. The last speaker for this session is Mr. Mohammad Nuruddin. This research topic is quality control analysis of diagnostic radiology equipment. Are you there?
I don't see him either.
None of them are there. So what? Those are the two last speakers for this session.
They got notifications. They even sent out a reminder earlier today. I mean, just like an hour ago.
Right.
That blows.
So shall we give them a couple of minutes, see if they join, or?
Yeah, let me see. Let me send them both a quick email. So you can sort of discuss amongst yourselves any of the two talks that we've heard this morning while I send these two colleagues emails. That's the best I can do.
So anybody from the audience wants to share some thoughts on the first talk about the solubilization of drugs in the presence of milk and infant formula? Please, the floor is yours. Or Samson, do you have something to share concerning?
Okay. Let me to what I have said so far. Let me add this to it. Okay. Now, another question that I will also have expect is, how can this pattern cope up the tissue homogeneity property? Okay.
Yeah.
Okay. Now, because we are saying that our fabricated phaton is suitable to that of water, photon, and also to do other commercial substitute photon material. Okay, which I've said from the introduction stage that the commercial substitute photon material that we are talking about here are simply the case of the solid water photon, then that of the PAPS, and that of the polyester. And they also has also been using as a substitute photon material before. And because of the deficiencies of WAS, then indeed WAS has been dropped to be continued using as substitute photon material. And then when you also look at these photon materials in this sense, okay, because the photon materials is what can be able to serve to mimic human body, is a social grade for mimicking human body. Okay, now, then it has happened in this sense is that for this photon material to cope up with tissue substitute property, then these properties are viable. The photon determination are a viable way to test the reliabilities of tissue homogeneity properties, such as the entropy, the contrast, the correlation, coefficient of variation, homogeneity, soft zone emphasis, short zone high grade level emphasis, and the high grade levels run emphasis, and the low grade level zone emphasis, etc. The constructed photon can have good physical, mechanical, and also dimensional solubility property. And their dosimetry properties can be similar to those of biological tissue, water, and other commercial tissue substitute photon material. However, for this photon to withstand tissue heterogeneity property, we have to evaluate and emphasize and analyze the photon to assist in choosing the appropriate parameter. And for us to quantify these parameters to two-month heterohomogeneities with well-defined conditions, such as the reconstruction technique, then acquisition, and the minimal volumes, and also segmentation. Now, before we can come in conclusion, for us to make use of the interconic acid, we have already did the NMR analysis for the interconic acid. Then we've also did the TGA for it. And also, we also have the result for DSA. Now, when you look at all these results now, and the solubility, that is talking about this case of the solid content of this photon material. If the solution on its own is not being soluble, then indeed, we're going to be talking about the case of the case of the hydrophonic of it. Then we also talk about the case that the homogeneity then have an issue. Then now we have a soluble solution. Then we also have the solid content of it must also be high. Then because according to Srf Setup in 2022 has also discussed that the solid content of a suitable tissue substitute photon material should be greater than, it should be within the range of 32 and above. Then our photon material now also have a solid content which up to 37%. Then also we also have to look at what is the moisture content of it. It has to be less before you can be able to meet up with the JISA 2015. Because the range of the solid content has to be within it has to be within the range of 5 to 10%. And our photon material, the moisture content indeed is within the range of 6 to 7%. Then we also have to look at the physico-mechanical property of it. That is what is the internal bonding strength of it, which has to be high. What is the modular of fractures of it? What is also the modulus of elasticities of the photon material, which also this has to be high. Then we also have to look at what is the thickness swearing and also the water absorption, and this has to be less. And
sorry, Samson, I just want to double check if one of the other speakers are around. Ibrahim, okay. Are you there?
Ibrahim, yeah, I guess he just signed in.
Okay, please could you share your screen and start your talk?
Or I don't know, is this the same one? Yeah. Or maybe this is not the same person. Not the right person. It's Ibrahima.
This is Ibrahima Gom.
I think that's not the same.
Yeah, it should be Ibrahim Bello.
Yeah. That's a different person.
Yes, hello.
Hi. Are you giving a talk?
Hi, yeah.
There's a different spelling of the.
Sorry?
Are you ready to give a talk today? Were you giving? You're not. You're not Ibrahim Bello, huh?
Yeah, I am supposed to give a talk today.
Yeah. What is the title of your talk?
Because I didn't receive any information about my talk. I submitted a abstract, but I didn't receive any feedback.
Is the title of your talk radiological assessment of cement particles?
Yeah, the title of it is a biosynthesis of nickel oxide nanoparticles using the flower, the seed, and the leaf of Moringa oleifera.
I do not see that talk anywhere.
That's not the same.
Yeah, I didn't receive any information about my talk.
I don't.
I submitted an abstract, but I didn't receive any feedback.
I do not see a title, a talk of that title in the system anywhere. So, I'm searching the abstract system and I do not see a talk of that title. There were a few rejections. I don't even see it there. All right, here actually. I did not see a title of that talk in the system. Chart, are you here? All right.
He's not.
He's not. So are you ready to give your talk right now?
Right now.
Okay, let's do it. What do you think?
No, right now.
Yeah, I think we should go for it.
No,
yeah. Okay.
I don't think so.
Yeah, go ahead. I will make you so you can share your screen.
Sorry?
You can share your screen. You can give your talk for 20 minutes right now.
No, it's not possible because I didn't prepare it. I have it in another laptop.
Oh, all right. Okay. Then I don't know what to do at this point. I guess the only thing to do is probably just end the session. What do you think, Emmanuel?
We end the session. The next session will be the biophysics and maternal health, which we start at 15:00 GMT +2, and then we wrap it up with the development of the future of biophysics in Africa. So we want to thank the two speakers for today. See everybody later today.
Okay.
Thank you.
Thanks, everybody.
Yeah, thank you.
Hey, Emmanuel, are you still here? Trevor, are you still there?